Hi guys! So the limits and continuity video is going to start out with just simple evaluating limits. So things you need to know, the NTK for limits. If the limit from the left and the limit from the right approach the same number, then the limit exists. If the limit from the left is different from the limit from the right, then the limit does not exist, right? Mean Girls style. So need to know. We need to know about right-sided limits and left-sided limits. So taking the limit from the right side means I'm going to have that positive sign on my number that I'm taking the limit to. And on my left-hand side, it's going to be a negative. So that's going to tell me if I'm taking the limit from the right-hand side, meaning I'm coming from the right. So for example, in number 1 in my graph that you do have to draw in on your guided notes sheet, when I'm going to come towards here, I'm coming from the left. So this would be the limit from the left as x approaches 1 would be, so the limit as x approaches 1 from the left of f of x is going to be 1. And the limit as x approaches 1 from the right, sorry it's a little sloppy, getting there, as I approach 1 from the right is negative 1. So since the limits are not the same from the right and left, this limit does not exist. So DNE does not exist. Now let's try the limit as x approaches 2. So the limit as x approaches 2 from the left of the function, well, from the left I'm approaching this way, is going to be, it looks like about negative 3. Whoa, what is that? And then limit as x approaches 2 from the right of f of x is, now I'm coming from the right side, I'm also approaching negative 3. So even though there's no functional value at 2, the limit as x approaches 2 is negative 3. Foreshadowing to later, this would not be continuous because the functional value is not equal to negative 3. Alright, so if we're going to solve limits analytically, then we're going to substitute the number you're approaching into the function, and you should get an answer. If you don't get an answer, you get what's called an indeterminate form. An indeterminate form, for example, could be like 0 over 0 or infinity over infinity. So then you have to rearrange the function so that we don't get an indeterminate form. So a couple ways to do that is, number 1, by factoring. So let's do an example. Now I'm going to probably go into the space that I have for the other 2 examples, but you're going to make sure that you put your space in the factoring side, and then I'll erase and put the one for complex fractions. You should be able to fit it. Mine's a little harder. Okay, so I'm going to first prove that this is an indeterminate form. So if I take the limit as x approaches 1 of just the top, x squared minus 1, then I plug the limit in, 1 minus 1, 1 squared is 1, 1 minus 1 is 0. And on the bottom I have the limit as x approaches 1 of x minus 1, plug in 1, 1 minus 1 is 0. This proves 0 over 0. Okay, now I can do some factoring work. So x squared minus 1, I'm going to change this limit as x approaches 1 to become x minus 1 times x plus 1. I'm just factoring using difference of 2 perfect squares, dots. And x minus 1 goes on the bottom. Okay, so now see what happens here. X minus 1 and x minus 1 cancel out, and I'm left with the limit as x approaches 1 of just x plus 1. Now when I plug in 1, 1 plus 1 is 2, so I could say that my answer is 2. That's with factoring. Alright, now let me erase this. Now let's try an example using complex fractions. So say for example, and I'm going to write it up here, but you're going to write it down where it says complex fractions. Say I had the limit as x approaches 0 of 1 over x plus 5 minus 1 over 5 all over x. Now this is a complex fraction because it has little fractions built inside of this big fraction. So I'm going to first plug in 0, and when I do that, I get 1/5 minus 1/5 is 0. So on the top I have 0, and on the bottom I'm also going to have 0. Now if I was writing this on the AP, I'd make sure to show the limit as x approaches 0 of the top, 1 over x plus 5 minus 1/5 is 0. The limit as x approaches 0 of x, the bottom, is just 0. This implies 0 over 0. Now, that you have to show on a free response question. If this is a multiple choice, oh no. We're just going to say 0 over 0, move on, do some complex fractions to get rid of those little fractions inside of the big fraction, and hopefully this will go back to being just a simple limit question. So let's see. I'm going to multiply both the top and bottom, each of these fractions. I'm going to put this 1 over 1, make it a fraction. I'm going to multiply by the common denominator. In this case, the common denominator, they have nothing in common, so I'm going to just multiply them together. So everything, 5 times 1 is 5 times x plus 5. Every numerator is going to be multiplied by 5 times x plus 5. Sorry, I'm writing in the words here, so it's not very neat. Okay, so what happens? This x plus 5 in the numerator cancels with this x plus 5 in the denominator, so I'm left with just 5 times 1 on top, which is 5. Minus this 5 here in the numerator cancels with this one in the denominator, so I'm left with x plus 5 times 1, which is just x plus 5. All over, now this nothing's going to cancel in the bottom, so I have 5x times x plus 5. And I'm going to copy down my limit statement, because I don't want to lose any points on that. X approaches 0. Okay, so now let's try plugging in 0. So I can simplify this more, or I can just try plugging it in. Why don't I simplify it a little more, just so we get in the habit of it. So 5, I'm going to distribute that negative. I have negative x minus 5. That negative 5 is going to cancel with that 5, so I'm going to be left with negative x on top. Copy down my limit statement. And on the bottom, we have 5x times x plus 5. I'm not going to distribute that because it's just going to make my life harder. Look at this. This 5 and this 5, they're gone, right? Let me erase these. So I'm left with negative x on top, but I also have an x on the bottom. It's all multiplied together. So those x's cancel. This just becomes a negative 1. So I'm running out of room, so I'm going to just erase this. We have negative 1 on top. We have a 5 still left on the bottom. Now let's substitute in 0. So on the top I have negative 1, and 5 times 0 plus 5 is just 5. So 5 times 5 is 25. My limit is just negative 1 over 25. Okay, and another technique. So that's complex fractions. Now let's move towards multiplying by the conjugate. This is for when I have a square root or a radical. So again, write this in where it says multiply by the conjugate in that example. That's this example. I just don't have enough room to, put it down that far low. Okay, so this has a square root in it. If I plug in 0, what happens? So if I take the limit of the top, limit as x approaches 0, on the top is the square root of 4 minus 2, which is just 0. Limit on the bottom, limit as x approaches 0 of just x is just 0. This gives me the indeterminate form, 0 over 0. If this is a free response question, I'm going to prove it just like this, and then I'm going to continue. If it's not a free response question, I'm saying, okay, 0 over 0, move on, do something about it. So we're going to multiply by the conjugate. The conjugate just means the opposite, right? So let's multiply. What's the opposite of square root of x plus 4 minus 2? It would be the square root of x plus 4 plus 2. And I'm going to multiply top and bottom by the same thing. And so what happens here? So remember, this is like a binomial times a binomial. So this, if you want to FOIL, if you want to do box method, if you want to distribute, that's fine. When I do this, I'm going to multiply these two. I have square root of x plus 4 times square root of x plus 4. The square root squared, because there's two of them, is just x plus 4. And then I have my insides, I have negative 2 square root of x plus 4, but then I have my outsides, I'm going to have a positive 2 square root of x plus 4. Those are going to cancel. And my last but not least, I have my two outsides, which are minus 4. Then on the bottom, I'm going to leave it just the way it is because chances are that x is going to cancel out, which is going to help me out a lot. Because right now, multiplying by a 0 on the bottom is going to make it still go to 0. And I don't want that. Okay, so let's clean this up. So we have 4 minus 4, that's gone, that's 0. X is going to be the only thing left up top, so that x can cancel with that one. So I have the limit as x approaches 0 of 1 over the square root of x plus 4 plus 2. Okay, now let's substitute in the 0 and see if I did enough to get my answer. So I have the square root of 0 plus 4 is square root of 4 plus 2 is going to be 4 and 1. So my answer is just 1/4. Okay, so multiplying by the conjugate, another way to solve limits analytically. Now the last way that we can manipulate these limits is by L'Hopital's rule, which you, side note, don't learn until after you learn derivatives, right, because it involves derivatives. So it wasn't in this unit, but I'm going to put it with this because it's important for both when x is approaching a number or infinity and you get that indeterminate form. So first things first, you have to prove that it's indeterminate. So expect this on the AP. You have to prove that the limit of the top and the limit of the bottom are going to give you that indeterminate. So the cosine of pi over 2, so cosine x over x minus, oh, I just want to do the top. Let's get rid of that. Okay, so I'm just doing the limit of the top. So the cosine of pi over 2, remember pi over 2 is 90, that's going to give me 0. And the limit of the bottom as x approaches pi over 2 of x minus pi over 2 is also going to be 0. This proves an indeterminate form, 0 over 0. You want to write indeterminate on your paper, and then you can proceed with doing L'Hopital's. Now for L'Hopital's, we take the derivative of the top and the derivative of the bottom separately, right? There's no quotient rule here. This is derivative of the top, derivative of the bottom, and then you reevaluate the limit. Sometimes you do have to do this more than once, so be ready for that. So first of all, you got to prove that it is indeterminate, and then we're going to say, okay, so now let's take the derivative of the top. So limit as x approaches pi over 2 is going to stay the same. The derivative of cosine is negative sine of x. And the derivative of the bottom is going to be derivative of x is just 1 minus 0 because that's just a constant. So now I have just the limit as x approaches pi over 2 of negative sine of x. If I plug my pi over 2 in now, I'm going to get sine of pi over 2 is 1 multiplied by the negative, so it's just negative 1. Okay, so keep in mind, if L'Hopital's gave me another indeterminate form, so like a 0 over 0 or infinity over infinity, then I would have to do it again, and I would keep doing it until I got an actual answer. L'Hopital's rules can be used for when x approaches a number, like pi over 2, or infinity, so it's going to come up again in the next part. Alright, part B is limits to infinity. So first we talked about evaluating limits both analytically and graphically. Now I'm talking about infinity. So as x approaches infinity, that means that x is growing without bound to the right because it's positive infinity. So for example, something like that. It's growing without bound. As x gets bigger, it's growing out to infinity. And then as x approaches negative infinity, that would be like something like that. As x grows out to the left, to the negative side, it's approaching negative infinity. Okay, so notice what happens here. This forms a horizontal asymptote. So if we need to find a horizontal asymptote of a function, we need to just say, okay, take the limit as x approaches infinity and as x approaches negative infinity. So here's my horizontal asymptote. Now when you're finding limits to infinity, we use that expression that everyone loves, Bobbio Bottineau eats DC. So Bobbio, bigger on bottom, y equals 0. Bottineau, bigger on top, there's none or the limit does not exist, or however you want to interpret that. And then eats DC, exponents are the same, divide the coefficients. So when I'm talking about bigger on bottom, bigger on top, I'm talking about the exponent of this rational function. Remember, rational functions are just polynomials put into fractions. So let's do an example. We're going to do example 1 here. So say I have the limit as x approaches infinity of 3x plus 1 over 5x minus 4. Okay, so I look at the exponents. The largest exponent on top of each one is 1. Exponents are the same, so it's eats DC. Exponents are the same, divide the coefficients. So the 3 divided by 5, the limit of this is just 3 over 5. Okay, so that's the eats DC. Let's try another one. If I have the limit as x approaches infinity of 6x squared plus x over 2x minus 5, then okay, so now I'm looking at these exponents. I have 2 on top, I have a 1 on the bottom, so it's bigger on top. If it's bigger on top, that means the limit does not exist, or there's no limit, or it's infinity. We're not going to worry about it. It does not exist. And then let's do an example 3. So the example 3 is the limit as x approaches infinity. And remember, actually, you know what? Let's make this negative infinity. Negative infinity, positive infinity, it doesn't matter. These rules apply to both. So x plus 1 over x squared plus 3. This one I'm looking at my exponents of my variables. I have a 1 here and a 2 on the bottom. So it's bigger on bottom. If it's bigger on bottom, Bobbio says then the limit is going to go to 0. Okay? The top. Now, as I mentioned before, L'Hopital's rule can also be used with limits to infinity too. So again, you want to make sure you show the indeterminate form. Most popular indeterminate forms are 0 over 0 or infinity over infinity. Something gets really, really big on both the top and the bottom. That's infinity over infinity. But these are also indeterminate forms, which are just good to know on the back of your mind that like there are other ones. They're just not as popular. So first things first, I'm going to prove that this is indeterminate. So I'm going to say, okay, limit of the top is limit as x approaches in negative infinity of x squared. So as x approaches negative infinity of x squared, remember x squared, here's the graph of x squared, right? Oh, that's not a graph of x squared. Let's make that cross at the origin, sort of. All right, it's a sketch. So anyways, as x approaches negative infinity, that's going this way. What's happening to the graph? It's going up to infinity, right? So that is approaching infinity. Now if I take the limit as x approaches negative infinity of e to the negative x, now if I think about the sketch of e to the negative x, that's going to look something like that. Again, sketching, sorry. Okay, so as x approaches negative infinity, again, this is going up to infinity. So this proves infinity over infinity, which is an indeterminate form. And you want to actually write that. It's indeterminate. Okay, now let's use our L'Hopital's rule. So L'Hopital says I'm going to take the derivative of the top and the derivative of the bottom separately. So limit as x approaches negative infinity, the derivative of the top is going to be 2x over derivative of the bottom. So I have e to the negative x. The derivative of e to the negative x is e to the negative x. But because it's a negative x, I have to do the chain rule. And the derivative of negative x is negative 1. So that's negative 1 e to the negative x. Now if I plug in infinity now, it's still going to be infinity over infinity. 2 times infinity is still infinity. And e to the negative infinity times negative 1 is still infinity. Or negative infinity. These are actually both negative. And still indeterminate. Negative infinity over negative infinity is one of those not as popular ones, but also if you think about it, a negative divided by negative is a positive, so they're going to cancel and become infinity over infinity anyway, which is another indeterminate. I'm abbreviating. So I'm going to do L'Hopital's one more time. The limit as x approaches negative infinity, again take the derivative of the top is 2, and the derivative of the bottom, now I have, again, e to the negative x is just e to the negative x. Chain rule for that negative x, so it becomes negative 1. So I'm multiplying negative 1 times another negative 1, which is just going to be positive. So I have 2 over e to the negative x. Okay, so if I plug in negative infinity, now I have 2 over negative infinity. When negative infinity is in the bottom, or a really big number is in the bottom of a fraction, that means this whole fraction goes to 0. Because it's bigger on the bottom, which forces the fraction to become 0, right? So the limit is just going to be 0. Very quickly, don't worry, not all the videos are this long. I just want to talk about properties of limits. They come up, and they come up again and again throughout the whole course. So it's not really something that you should be too afraid of. The constant multiplier rule, if I multiply by a constant, when I'm taking a limit, that limit can be multiplied by that answer of the limit. And if I take the limit of a number, it's just a number. That's really important. Like if I take the limit as x approaches 2 of 10, it's just 10. Because remember, this is like the graph of y equals 10. And as x is at 2, it's still at 10. So it's just a number. When I take the limit of a number, I get a number. That's probably the most important and useful rule that you're going to see so far. Adding, the addition rule, the limit holds over addition, the limit holds over multiplication, the limit holds over division as long as m is not equal to 0, so as long as the bottom limit's not going to equal to 0. It holds over exponents, and it holds over compositions. Like I said, not super important, but just good to be aware of. This is definitely important. When I take the limit of a number, it's just a number. All right, made it to the final part of this section. So continuity. Continuous. To prove a function is continuous, we need three things. First of all, we're proving it at a point. So they're giving me a number to prove it at. They're going to ask me to find if the limit as x approaches c of f of x exists, meaning the limit from the left is the same as the limit from the right, right? They're going to ask if f of c exists, if that point is there. And then, is the limit as x approaches c of f of x equal to the functional value at c? So here's my example one. Like I said, same thing with this guided note sheet. You should be able to fit this in example one. I just don't have space to do example 1, example 2, and example 3 all on the same slide. Okay, so this is example 1. I want to prove that this is or is not continuous. So I'm going to go down my list of this with this graph. So number 1, does the limit from the left equal the limit from the right? So the limit as x approaches c from the left of f of x is equal to the limit as the x approaches c from the right of f of x, because as I approach left, it approaches this hole, and as I approach right, it approaches this hole. Okay? Yeah, I'm sorry. I'm assuming that this letter is C right here. Which this implies that if it's the same from the left and it's the same from the right, then I know that the limit as x approaches c of f of x exists. Okay? So step 2, does f of c exist? No. F of c does not exist. There's a hole there, right? And there's no other point. Like if there was a point up here, then f of c would exist. But f of c does not exist. So hence, f of x is not continuous. Okay, so that was not continuous, example 1. Let's try example 2. All right, so for example 2, again, I'm assuming that this is C. This is the point I want to prove is continuous or not continuous. So number 1, does the limit exist? So this is actually very similar to the last one. The limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x. Therefore, the limit as x approaches c of f of x exists. So my first condition is satisfied. Step 2, does f of c exist? Yes, it does. F of c is right there. There's a functional value there, right? Like I can give it an actual number. Number 3, is the limit as x approaches c of f of x equal to f of c? And the answer to that is no. Hence, f of x is not continuous. Because the functional value is down here, the limit is going to be something positive. Is not continuous. All right, last example. What do you think this one's going to be? So this is example 3. I'm going to prove that this one is continuous. So first and foremost, step 1, I have to prove that the limit exists. So does the limit from the left equal the limit from the right? The limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x. Therefore, the limit as x approaches c of f of x exists. Right? All right, step 1 done. Step 2, does f of c exist? Yes, there is a functional value at c. It's right there. And step 3, does it equal the limit? So does the limit as x approaches c of f of x equal f of c? Oh. There we go. And the answer is yes, right? Because the limit is going to be around here, and the functional value is the same. So hence, f of x is continuous. All right, so those are my examples for continuity. So proving continuity, you need 3 things. The last thing we got to talk about is just discontinuity. So when there's a discontinuity, remember there was 2 types. There was the removable discontinuity. That's when one point is removed. So for example, on a graph, if I have a function that just has a hole, basically, and then I have maybe a functional value up there, that's a removable discontinuity. It removed only one point of the function. But if I have a jump discontinuity is when more than the point moved. So like the whole function moved. So for example, if I have a function that goes like that and then one that continues this way, that's a jump discontinuity, because in order to make this continuous, this whole piece would need to be moved up. So that's a jump discontinuity. And then we also talked about vertical asymptotes and holes. Vertical asymptotes is when if f of x approaches infinity or negative infinity at some x value. So say you're doing the limit as x approaches 2 of some f of x, and you get infinity, that means there's a vertical asymptote at 2. So the way to distinguish if it's a hole or an asymptote is by using the actual function. So here's an example. If I have the limit as x approaches 1 of x minus 1 over x squared minus 1. Well, if I plug in 1, I'm going to get 0, 0. It's indeterminate. So I'm going to factor this and change it up. I'm going to have the limit as x approaches 1 of x minus 1 over x minus 1 times x plus 1. When you cancel in the bottom with the top, that x minus 1 means that at x equals 1, there is a hole. Because I canceled it out. Now there's that missing piece, right? And then at x plus 1, since that's the denominator, at x equals negative 1, that means there's a vertical asymptote there. So if you cancel out the expression with something in the top, whatever that is, when it's set equal to 0, that's going to be your hole. When I'm left with an expression in the bottom, if I set that expression equal to 0, that's going to give me my vertical asymptote. So x equals negative 1 will be a vertical asymptote. All right, so that wraps up limits and continuity.